So we'll continue with waves. But one of the things I want to do is when we talked about, we're going to get to electromagnetic waves today, actually. But when we talked about the two strings attached, and we talked about this, and maybe, the combination doesn't matter. This is a different gauge string, maybe, or just even different material. And, I'm just trying to distinguish one string from the other. We had two boundary conditions, and waves, the way you get physical solutions, are just all about boundary conditions. Okay, so this is the point z equals 0, and we wanted the waves to be continuous. That means if you, right? This means if the string was distorted in any way, well, over here, they actually made contact. Yeah, the string is not breaking. This is just continuity. And more importantly, in this case, we never talked about in detail why, but we wanted the slope to be continuous. So the derivative, the slope to be continuous, it should be smooth, right? But now imagine, I'm not going to do the whole problem. I just want to tell you how to recover the boundary conditions depending on the circumstance. Suppose you have a string and it's knotted and a different string is tied to it. Okay, this is z equals 0. Okay, so now when you have a wave, this knot, say, it goes up, but this knot itself has some mass. So, and it's lifting this mass around. So you can imagine that the derivatives don't have to really be smooth. See, it's not differentiable, you see? Or it could even be like, so if this has a mass, this condition should be, of course, true. Yeah? But there is a net force on the mass. So if you look at the mass over here, there's a force in this direction, perhaps, and there's a force in that direction. And we know these two forces. This is T times dF dz, 0 plus minus dF dz, 0 minus. This is the left force times the right, subtracted from the, sorry, the right force minus this one. That should be equal to MA. That should be equal to M times, again, evaluated at 0. Now you try to solve the same problem with this boundary condition, it can get to be very complicated. And if you had the energy as a special project, it's not impossibly difficult. It's just you have to deal with phase and complex numbers and so on and so forth. You can carry it through with a little bit of time. We don't want to spend too much time here. We will see somewhat of an analog in the case of electromagnetic fields, and that is what is most relevant to us. So we're just going to move on. I'm just mentioning that these boundary conditions all boundary conditions only apply under certain circumstances. And for each time you change the circumstance, you have to look at the physics and try to carve out the boundary conditions. Okay? We will have an analog of certain differences. We will have light going from one medium into another, from air to glass or air to water and vice versa. So we'll find all of this in the context of E&M. And because this course is E&M and we have E&M in mind, I'd like to press on. Yeah, but you can see how boundary conditions play a very important role. Fine. So again, let me just do a few more things. You have a wave. This is the z-axis. And I'm going to be consistent with Griffiths, and I'm going to talk about polarization. You could have a wave like this. Yeah? And Griffiths denotes this as a vertical wave. And it's a vector. And it's a complex wave. Now, if I am completely true to the notation that we've been following, gosh, I would do that. But that gets a little cumbersome. So let's assume that things are complex, and when we have to take the real part, we actually force that conversation. Okay. So, but now that I put this tilde over here, just for once, I'm going to put this tilde over here. You're going to have a complex number, and then e to the I kz minus omega t. But the wave itself is in the x direction, so I'm going to make it an x hat because I made this a vector. Yeah? Because it's actually, things are actually going in the vertical. Again, I know it's confusing, but
it's kind of like an XZ plane.
It's in the XZ plane. Yeah. Usually X is not chosen as the vertical, and Z the horizontal. But then you can have a different wave, and I don't know how to draw this properly, but it could be in the Y. Oh, that's not too bad. I'm going to leave it there. In the YZ plane. Okay. Don't want to mess with that. So, horizontal. And you can have, and maybe subscripts now, not so important. But maybe this should clarify by putting tilde over here that this guy is actually complex. So it's just some constant, I k z minus but it is kind of arbitrary when you think about it to choose a wave to oscillate about the x-axis or the y-axis. It could be anywhere in between. These are called, and we'll distinguish it from other kinds of polarization, these are called plane polarization because it is not oscillating in a certain plane. But in general, what can you have? For a plane polarized, that's the language, that's the jargon. F is equal to A tilde e to the I kz minus omega t n hat, where what is true? Plane polarized, let's say this, transverse. because remember, look, Z is perpendicular to X and Y. So if it is anywhere in between, it is still perpendicular to the Z axis. Yeah? So that means N can be written as some, it's a unit vector, sine theta, y hat. And this theta is referred to as the polarization angle. And it's easy to control the polarization of an electromagnetic wave. We'll do this. We'll have a demo in class. Let me cover a few more topics. Let's talk about reflection and refraction, and then we can do it. But polarizers are easy. Your sunglasses are polarized, and so on and so forth. Okay. There are lots of crystals, materials that will only allow for electromagnetic wave in a certain polarization to pass through. And you can simply rotate that material, a film, and then only that angle will pass through. And gosh, polarization can be written using any arbitrary coordinate system or linear combination. I don't mean coordinate system. Linear combination of vertical and horizontal, right? So but there are other ways of writing it. There's elliptical polarization. We won't talk about it that much. We don't do much with polarization, although we will. You can see the slightest thing can complicate the issue visually. Mathematically, it's just as easy. You could have circular polarization. So let me clarify this. So this is plane polarization. So plane versus circular polarization. This is, I think, part of a problem. I'm not sure if I did the whole part. It is problem 9.8. Okay. So suppose you have a wave, and it is cosine kz minus omega t x hat plus two waves with the same amplitude that are off. This looks very harmless. And two waves, one just out of phase of the other, same amplitude. This is the real component. I'm not using e to the I. Yeah? Okay. So let me simplify this. Cosine kz minus omega t x hat. Cosine of 90 plus theta is minus sine theta. So it is minus a sine kz minus omega t y hat. So what I'm going to do is graph this in the xy axis to see what it looks like. So let me do this first at t equals 0. So then I have a cosine kz minus a, oh, this is in the x hat direction, minus a, you know what, let me factor out the a. Cosine kz x hat minus sine kz y hat. So I'm going to graph this in the xy plane. So there are two things I want to do. First of all, I want to just see what, I'm going to graph this, so I need to know how long this is and how long this is. So I'm going to pick an arbitrary angle. Doesn't really matter. We don't know what kz is. And I'm going to call this kz. So that means this much is, if this is like A, this is A cosine kz, correct? And this much, and that is A sine kz. Now let me draw the xy plane. And I'm going to graph or plot the point F. So in the x direction, I need to go A cosine kz long. So I'm going to do this and mark this over here. Then I need to do a minus kz in the y direction. So I do this, and hopefully I won't squish my fingers, and I bring it over here. And this is f, and t equals 0. Yeah? Since I need that graph, I'm going to wait a little longer. Well, how long am I going to wait? I'm going to wait when, so this is t equals 0, and omega t equals pi over 2. Just to see what it does a little, because when I do pi over 2, it's easier to plot. Nothing nice about, nothing specific about pi over 2. It's that when you sine of 90 plus theta, cosine of 90 plus theta, you know the formula. Which means t equals pi over 2 omega. At that point, we have, this is cosine of kz minus pi over 2 x hat minus sine of kz minus pi over 2 y hat. And gosh, if I remember trig identities, I would do well, but I don't. Cosine of 90 minus theta is sine theta. Sine of kz x hat. You can look this up, and this becomes cosine. Cosine kz y hat. Now let me graph this point to see, if you look at the wave, how is, what's the wave doing? You'll see it is changing its plane of polarization. So the wave is not going back and forth like this. That would be the case if it was linearly polarized. A simple trick like this, it does something entirely weird. So sine of kz in the x hat direction. So I'm going to pick sine of kz and come over here. Then it's cosine of kz in the y hat direction. Gosh. Yeah? You see what the plane is doing? It is rotating. The plane of the wave is rotating. So it's like you can have the same kind of wave, which is just totally weird to what we originally thought we had. Now, for the life of me, I cannot graph this on the board. So what do I have for you? What it looks like. So just in case people are wondering what it looks like this. So although these are simple vectors in trigonometric functions, if you're confronted by actual physical problems, oh, that's a good move, Chip. You just took a picture of that
I can take a picture of it.
page, and then it's part of your notes, right? Yeah, because paper notes are obsolete. Fine. So all you have to remember here is things can get complicated. Complicated, but with patience and analysis, we can solve them. It's, at the end of the day, just trigonometry and basic vectors. Fine. So these are called circular polarization. Yeah.
Do we see those in nature?
Yeah. Gosh, now that you put me on the spot, I can't think of. I don't even know if which way sunlight is polarized. Could you Google it if you have? I mean, I do know it, but I can't think of it right now. Also, I invite you to ask Dr. Sanders about, show you some demonstration about polarization. I bet you he can set it up for you.
No to sound.
Huh?
There's a no to sound. Because the vibrations and sound waves are in a direction parallel to the
Right. It's a sound waves are longitudinal. These are transverse waves. I'm talking about sunlight.
sunlight.
Yeah, sorry. Yeah, sunlight.
So it's both circular and linear polarization of sunlight has been measured.
Yep, there you go. So both circular and linear. Thank you. Well, we're studying E&M, so we better have electromagnetic waves. So, on the one hand, I'm going to do this. Del cross minus dV dt. From Faraday's, so in vacuum. What does that mean? Rho equals 0 and J equals 0. This is nothing more than, well, minus dB dt from Faraday's law is nothing but the curl of E. And curl of E from the inside cover of your textbook, please locate it if you're able, is, well, if you located it, this is exactly what it would read. Minus del squared E. Yeah? This is 0. So then I can do minus d dt of curl of B. Why is divergence of E 0? There's no rho. Good. Divergence of E equals negative del squared. Now, remember this is a scalar operator. This is what makes it a vector. Del squared. In Cartesian, which is easy to write. Yeah, that's what it is. Now, del cross B is what? Normally there'd be a J term, mu naught J, that goes to 0. And then you get mu naught epsilon naught dB dt. dE dt, sorry, if it's del cross B, it's the other one. Mu naught epsilon naught dE dt. Well, that's, let me write it over here. And what you get is write it in the way I would want to write it. This looks like a three-dimensional wave equation with speed what? C. Remember? Kind of neat. In exactly the same way. You play around, you start with the del cross B, you will get for you to, so this is an interesting, I mean, it's a nice equation. You know, like I said, I like equations that have space and time on equal footing. Again, c times t is distance. So this is two derivatives of distance. This too is a two derivative of distance, calibrated by light and time. The only difference is, of course, space has plus, time has minus. You cannot get rid of that feature. Yeah. That is a problem for so many things. But you have uncoupled E and B. We have uncoupled E and B, meaning the equation for E is separate, and equation for B is separate. We'll soon see that that doesn't mean that E and B are actually coupled. When we look at Maxwell's equations, imply this. But this doesn't, by itself, will not imply all of Maxwell's equations. You have to go back to Maxwell's equations. Okay? But this must be true. That's what we're saying. And they look like decoupled waves. So, for example, what will they look like? What will an electric and magnetic wave look like? So let's consider, for example, a wave that, again, we wanted to propagate in the z direction. So what we want is a wave that's propagating in the z direction. With that in mind, I can write E z t equals E0, some vector e to the I kz minus omega t. And gosh, I'm not writing any phases, so these are complex vectors. And I can do the same thing with B. Divergence of E, So this is what I mean by, there are some restrictions on E0 and B0. The way we have written this, there's E and B are not related to each other at all. That's not true. Divergence of E is 0. What is the divergence of E? Easy vector to take, implies E0 Z. Times I k e to the I. This is why we write everything in terms of E. If you're taking derivative with respect to Z, the I k just comes out. That is 0. That means E0Z is equal to 0 because these guys are not 0. Yeah? Fine. Well, similarly, divergence of B equal to 0 will imply B. So these two vectors do not have a Z component. What does that mean? If the wave is propagating in the Z direction, E and B is perpendicular to Z. It's transverse, right? From freshman physics, I know we haven't discussed it in this course. You know what's the difference between transverse and longitudinal, right? Yeah. So here the waves are propagating this way, but really the E and B is in this plane, perpendicular to Z. Then comes the actual relationship between these two, additional relationship between these two vectors. Curl of E is equal to, well, let's just take it, x hat, y hat, z hat, partial with respect to x, partial with respect to y. So we've discussed this notation, right? And then I have E0x e to the I, E0y e to the I, and this is 0, and these two are complex numbers. I don't have enough space, so I'm not writing kz minus omega t. So from this times this is 0, minus this times this. So I would get minus I k E0y e to the I kz minus omega t. Let's spend some time on this. Let me first write this. E0 x e to the I kz minus omega y hat. Is that true? Is this completely clear to you, or should I pause and explain? It is? Yeah. So only the z derivatives will come out. But on the other hand, del cross E should be equal to minus dB dt. So that is what? dt has a minus already, so the minus goes away. I would get b0x complicated, complex, the x component of b0, and what comes out? I omega x hat and plus I omega b0 y hat. Yeah?
So whenever we take those derivatives, are E naught and E naught, they have no dependence on position?
No. It's just a phase factor. It's just a vector. No, sorry, it's the complex amplitude, which means that it's the amplitude plus the phase. And phase is sort of like the initial angle. It's initial, it's fixed. It's time independent. So all we have to do is compare these two, because this is equal to that, so these two components have to be equal. So we get minus ik E0y complex is equal to I omega B0x. Let me cancel off the I. Which means E0y, or let me write B in terms of E. B0x is equal to minus k over omega E0y. And what is it? Ik E0x should be equal to I omega B0y, or B0y equals k over omega E0x. Correct? Well, correct. Good point. Yeah. Again, this is the reason we wrote everything exponentially, because then the function dependence cancels off. So these two equations, if you look at this little while, you will realize that this is nothing more than the curl. One is the curl of the other. Let me write it explicitly. B0 tilde equals k over omega. It is c hat cross, hold on. Let me put the tildes. Just take the curve, and you'll find that to be the case. What do you notice from here? E and B are in phase. Correct? Whatever the complex factor is over here, it's the same complex factor. This is real. This is real. The amplitudes are different, but the phase factor is real. So 2 lessons learned. EM waves are transverse, and E and B are in phase. K over omega can be written in a different way. If you want to look at the speed of the wave, we know the speed of the wave is c. So if I said kz minus omega t equals 0, I would get zt to be equal to omega over k. Is that true? C over t is omega over k. Yeah? So that means this is c, the speed of the wave, which we have already confirmed. So I can also write this as b0 equals k over omega 1 over c, c hat cross so now I got it right the first time. Good chance I'll botch it up this time. This is my electric field. And this, so this is E. And this is my B. Yeah? Now what does that mean? At any point, what that means is at any point, this is my E. That's what it means. And at this point, this is my B. So it'll, the strength of E increases and decreases, and strength of B increases and decreases. Their amplitudes are not same. This is unit magnitude. This has the same magnitude as this one, but it's diminished by a factor of C. Yeah? And E and B oscillate perpendicular to each other in phase. And that is how plain electromagnetic waves propagate. You can have more complicated waves. We picked a nice wave going in the Z direction. Any questions?